Astronomers call this the Dark Ages. This period began around 380,000 years after the Big Bang, when the first atoms had just formed and the cosmic microwave background radiation spread throughout space. At that time, there were no galaxies, stars, or planets of any kind. The universe was shrouded in darkness, impervious to any form of light. Under the influence of gravitational forces, clouds of matter gradually coalesced together at an exceedingly slow pace. And thus, the first stars were born from this process. In the period from 200 million to 1 billion years after the Big Bang, regardless of what type the first stars were, they pumped a colossal amount of light energy into space. To the point where he nearly ionized most atoms in the universe by blasting electrons away from their nuclei. This event produced immense glowing gas clouds, setting the cosmos ablaze with brilliance. Over time, that light traversed the vast expanses of space. The first sources of light, formed over 13 billion years ago, can still be observed today as tiny bright dots through sufficiently powerful telescopes. The first attempt to observe the most distant regions of the universe was made in 1995, when the Hubble Space Telescope pioneered the use of the deep field imaging technique in astronomy. Over 10 days of observation, the Hubble Space Telescope focused on a tiny patch of sky equivalent to the size of a tennis ball when viewed from a distance of 100 meters. The selected area lies near the Ursa Major constellation and appears to be completely empty. No objects have ever been observed in this location before. However, after just 10 days of collecting light, the Hubble telescope captured an image showing 3,000 celestial objects. Most of these were small galaxies, located more than 10 billion light-years away from us. The famous photograph known as the Hubble Deep Field provided astronomers with their first authentic view of extremely distant and vast regions of space. Previously, observations from ground-based telescopes could only detect the most distant galaxies within a range of 7 billion light-years, equivalent to about half the width of the universe. These galaxies appear indistinguishable from modern galaxies. This has led astronomers to hypothesize that, somehow, galaxies formed relatively quickly and evolved into a stable state within just the first 6 billion years of the universe. Today, galaxies are classified based on their shapes. Elliptical galaxies have shapes resembling flattened and elongated stellar spheres. Meanwhile, spiral galaxies possess a flat structure, consisting of a central region containing stars and characteristic spiral arms extending outward. A barred spiral galaxy has a long central bar connected to its spiral arms. Additionally, irregularly shaped galaxies also exist. A vast number of small, distant galaxies in the Hubble Deep Field have demonstrated that today's large galaxies originated as mere clusters containing a few million stars or fewer. They have irregular or elliptical shapes and spontaneously evolve into larger galaxies through collisions and mergers with neighboring galaxies. As their size gradually increased, they eventually accumulated sufficient mass to generate a gravitational field strong enough to draw gas from the surrounding space into the galaxy. When strongly pulled into the galaxy, the gas enters orbit and forms a disk rotating around the central region of the star. When this disk accumulates sufficient gas, a spontaneous star formation process begins within it, enveloping the galaxy in brilliant stellar branches filled with new stars. Two distinct long spiral arm structures can form. Each of these structures reveals the activity of galactic energy within individual galaxies. First are the grand design spiral galaxies, with two major spiral arms extending from the galactic center. A giant ring of material, created by shock waves, is rotating around the galaxy's center. The ripples, also known as density waves, compress gas and dust as they travel, thereby triggering the process of star formation. Conversely, the second type of spiral galaxy, known as a flocculent spiral galaxy, consists of a chaotic spiral arm full of stars, which forms without the intervention of a density wave. When a bright star cluster is born, the stars closest to the galactic center complete their small orbit in a very short amount of time. Stars that are farther away take longer to fade. This causes the star-forming regions to stretch out, forming spiral arms. Thousands of these spiral galaxies cluster together, resembling a ball of yarn. If a spiral galaxy exists in isolation, it will continuously draw in and accumulate gas from the surrounding interstellar medium. Perhaps, sometimes it will swallow another galaxy that is much smaller. However, both of these processes do not alter its overall spiral shape. However, if it moves too close to a similarly sized galaxy and experiences a slight collision, that impact will destroy its delicate spiral structure. When these two galaxies merge, their original structures will completely disappear and form a giant LM-type star cloud, meaning an elliptical galaxy. And this tremendous collision also caused all the remaining gas in the merging galaxies to transform into new stars. The plan for an explosion that unexpectedly forms a star is called a starburst phenomenon. In the next few 100 million years, a series of brilliant star clusters will successively form until the gas supply is completely exhausted. At the heart of merging galaxies, dramatic and intense events are unfolding. Both of these galaxies contain a supermassive black hole at their center. These black holes will sink into the center of the merged galaxy and spiral inward, drawn toward each other. Their immense gravitational pull will interact, tearing stars apart and flinging others into eccentric orbits. Finally, the two black holes drew near and merged into one, releasing a tremendous amount of energy in the form of a shockwave that rippled throughout the galaxy. The newly expanded black hole will continue to devour any unfortunate gas clouds, stars, or planets that stray into its gravitational pull. During the first few million years after the merger, an immense amount of matter may have existed, and these merged galaxies would likely have evolved to become more rounded in shape. This galaxy is extremely active and radiates brilliant light. These microplastic particles once existed in overwhelming numbers and dominated the entire ocean, but now they have declined to the brink of near extinction. It is no surprise that the black holes, which are their energy source, have devoured everything within their gravitational field. Finally, when the primordial galaxy died, it transformed into an ordinary galaxy with a dormant central black hole. Cosmologists believe that the universe was formed with its current number of galaxies in this way. However, the nature of the initial step that forms stellar branches, as well as the origin of those clusters of a few million stars, has remained a mystery to this day. When the Hubble Space Telescope was upgraded with a new camera, astronomers tested it by observing a different deep space region. The Hubble Ultra Deep Field, as this image has been newly named, covers an area of sky about 1/10 the diameter of the Moon as seen from Earth and reveals images of 10,000 faint, small galaxies. Most of them appeared just about 800 million years after the Big Bang, which is truly astonishing. But there is still no sign of the primordial and isolated celestial bodies. They must be even farther away and too faint, beyond the reach of even the most powerful telescopes. Therefore, astronomers are forced to rely on the assistance of theorists. Users employ computers to simulate the formation ability of the first celestial bodies created by gravitational force. Now, it seems there are two possibilities. Either they are giant stars by our modern standards, or they are black holes that are busy sucking in gas and will emit extremely intense radiation when they stop being fed matter. Whatever they may be, they are objects that come together, forming the building blocks of galaxies and contributing to the universe's preparation for forming new celestial bodies. Because stars undergo these processes in different ways when they fall into a black hole. Therefore, identifying what the first celestial object was is of great importance to cosmologists, as it helps them understand the subsequent evolution of the universe. Of all celestial bodies, stars have the greatest influence on the formation of the universe's chemical composition. And no stars exert as powerful an influence as those formed earliest. During the cosmic dark ages, before the first stars ignited, the entire universe was but a vast ocean of atoms stretching everywhere. Approximately 3/4 is HIPPRO, 1/4 is heli, accompanied by a small amount of LITI, and no other elements have been affected. And computer models also indicate that this lack of diversity profoundly affected even the very next generation. Because gravity pulls gases together to form a star, it naturally heats up as the atoms are compressed. This heat counteracts the increase in compression pressure and must be released into space for the star to continue contracting. Calculations show that heavy chemical elements are extremely efficient at dissipating heat, while light gaseous elements struggle to release energy. Therefore, in the subsequent formation process, the emergence of elements heavier than lithium accelerated the contraction rate, allowing stars to form from relatively small gas clouds. This causes most stars to have a mass smaller than that of the Sun. However, during the cosmic dark ages, stars formed without the admixture of heavy elements to aid the cooling process. This meant they had to accumulate a much larger amount of gas for gravity to become strong enough to prevail. Therefore, the first stars in the universe were far larger than the stars we observe today, with masses that could be hundreds to thousands of times greater than that of the Sun. If such a giant star were in the Sun's position, it would be large enough to engulf all the planets in the solar system. First, it is believed that these primordial giant stars themselves were the chemical factories of the universe, where great nuclear reactions took place. They convert a portion of hydrogen and helium into other chemical elements and disperse them into space, contributing to the formation of new, smaller generations of stars. But there is a flaw in this theory. Nuclear fusion transforms hydrogen in one of two ways. Either through a series of collisions known as the proton-proton chain reaction, or by a reaction cycle called the carbon-nitrogen-oxygen cycle, commonly abbreviated as the CNO cycle. Between these two reaction chains, the proton-proton chain has lower efficiency. However, since the first massive stars contained no carbon to initiate the CNO cycle, they were forced to rely on the proton-proton chain. One obstacle is that the proton-proton chain reaction cannot generate enough energy to counteract the gravitational force in a star of such large size. Therefore, the star will simply collapse and become a black hole. A black hole formed in this way has a mass several hundred to several thousand times that of the Sun and will inevitably become the nucleus for the formation of a galaxy surrounding it. Essentially, this is a quasar in its formative stage. This explanation may not be entirely accurate, as the light captured from some extremely distant quasars, celestial objects that were already shining just about 900 million years after the Big Bang, has revealed a pattern of absorption lines. This indicates the presence of an ancient element that could only have been formed in the core of a massive star. Therefore, at least some stars must have formed before these quasars. After that moment, the first stars and black holes likely formed the primordial celestial objects. The only way to accurately understand the events of that ancient era is to find a method to observe that entire dark period, in the quest to detect the heat emitted by the first stars. In 2006, astronomers conducted an experiment using a high-altitude balloon. It is used to measure the infrared radiation emitted by the first stars, which has been shifted to radio wavelengths due to the expansion of the universe. However, the experimenters discovered that a mysterious radio wave barrier had deafened their detector. This signal interference is 6 times stronger than astronomers predicted and completely obscures observations of thermal radiation from the first stars. Cosmologists hypothesize that this mysterious radiation may originate from the most ancient stars in their death throes. They had a valid reason for making that inference, because when giant stars explode, their brightness can increase billions of times compared to normal. Therefore, it seems this is the first visualization of something, just after the dark period. Not an ordinary star, but a brilliant explosion marking the end of a star's life. Indeed, the most distant event we have observed to date is a type of celestial explosion known as a gamma-ray burst. The subsequent explosions appeared to release a source of energy even more powerful than any supernova ever observed in the modern universe, and further reinforcing the hypothesis that earlier generations had greater mass compared to the present, thus experiencing more violent deaths. Scientists calculate that when a giant star dies in a supernova explosion, it releases an immense amount of energy, equivalent to that of 10 trillion sun-sized stars. The vast majority of this colossal energy is released in a sudden gamma-ray burst, tearing through the fabric of cosmic space. If observed from Earth, we cannot know from which direction the next gamma-ray burst will originate. An incident occurs every day or two, but they always come from directions we could never have anticipated. Not only that, but astronomers must also be very quick to detect them in time. They traveled billions of years to reach us, only to depart in the blink of an eye. Despite their immense complexity, the spacecraft systems remain in a constant state of readiness. Upon detecting an outbreak, they can pinpoint the explosion within just 1 second, sending guidance signals so that orbital telescopes and ground-based observatories can point their lenses to the exact correct location. This gamma-ray burst, named GRBO 90423, currently holds the record for the most distant object ever observed. Calculations indicate that at the moment of its explosion, it was a staggering 13.1 billion light-years from Earth. This explosion was observed from Earth on April 23, 2009. Based on this, astronomers calculate that this celestial object exploded just 600 million years after the Big Bang. This makes it a prime candidate for the role of the universe's earliest star. Another strategy for studying the dark ages is to search for electromagnetic signals emitted by galaxies that existed in space at that time. Heterogeneous atoms have the ability to spontaneously emit radio waves with a wavelength of 21 centimeters. As this signal travels through the expanding universe, its wavelength is stretched to nearly 2 meters and can be detected by an ordinary radio receiver. But to process the acquired data, tens of thousands of receivers operating simultaneously along with a supercomputer are required. Astronomers are currently constructing such telescopes and expect to use them to map the distribution of the first celestial objects surrounded by hydrogen gas. A foreign atom can only emit radio waves when an electron moves in orbit around its nucleus. Because ionizing radiation from the first luminous objects knocked electrons out of atoms, the 21-centimeter signal vanished by the end of the cosmic dark ages. A silent radio bubble will form around each new celestial body, and these bubbles are expected to appear as black holes on the anisotropic cosmic map charted by the new radio telescope.